Here is the third part of the lecture. In this part, we shall discuss about types of wind turbines, wind farms, and relative merits of wind energy. The wind is a byproduct of solar energy. Approximately 2% of the sun's energy reaching the earth is converted into wind energy. The surface of the earth heats and cools unevenly, creating atmospheric pressure zones that make air flow from high to low pressure areas. A wind turbine extracts energy from moving air by slowing the wind down and transferring this energy to a spinning shaft, which usually turns a generator to produce electricity. The power in the wind that's available for harvest depend upon both the wind speed and the area that's swept by the turbine blades. There are two types of wind turbines, namely horizontal axis wind turbines and vertical axis wind turbines, as shown here in the picture. Although the vertical axis wind turbines have existed for centuries, they are not as common as the horizontal axis counterparts. The main reason for this is that they do not take advantage of the higher wind speeds at higher elevations above the ground as well as horizontal axis wind turbines. The vertical axis wind turbines, or VAWTs, have the main rotor shaft arranged vertically. One advantage of this arrangement is that the turbine does not need to be pointed into the wind to be effective, which is an advantage on the site where the wind direction is highly variable. It is also an advantage when the turbine is integrated into a building because it is inherently less steerable. Also, the generator and the gearbox can be placed near the ground, using a direct drive from the rotor assembly to the ground-based gearbox, improving accessibility for maintenance. On the other hand, there are some disadvantages too, which include the relatively low rotational speeds with the consequential high torque and hence higher cost of the drive train. The inherently lower power coefficient, the 360 degrees rotation of the airfoil within the wind flow during each cycle and hence highly dynamic loading on the blade. The pulsating torque generated by some rotor designs on the drivetrain and the difficulty of modeling the wind flow accurately and hence the challenges of analyzing the designing of the rotor prior to fabricating a prototype. The main types of vertical axis wind turbines have been shown here. The designs are Rotor Darius H, Rotor Darius Helicoidal, and the main parts of these vertical axis wind turbines are the upper head, guy wire, rotor blade, generator, gearbox, lower hub. The gearbox and the generator could be placed at the base portion of the wind turbine. Here are some pictures of the vertical axis wind turbine. Here in this slide is listed the relative merits of vertical axis wind turbines. The advantages of the vertical axis wind turbines are the generator and the gearbox can be placed on the ground. The structure is simple and there is no need of yaw mechanism to turn the rotor against the wind. These structures are easier to design and very ideal for small-scale wind energy. The main disadvantages of the vertical axis wind turbines are low to the ground where wind speed is lowest. Overall efficiency is low. These are not self-starting machines. These require guy wires and additional structural components to support the system, and sometimes the maintenance is cumbersome. The horizontal axis turbine is the most common wind turbine design. In addition to being parallel to the ground, the axis of blade rotation is parallel to the wind flow. Some machines are designed to operate in an upwind mode, with the blades upwind of the tower. In this case, a tail vane is usually used to keep the blades facing into the wind. Other designs operate in a downwind mode so that the wind passes the lower portion of the tower before striking the blades. The horizontal axis wind turbines, or HAWT, have the main rotor shaft and electrical generator at the top of the tower and must be pointed into the wind. Small turbines are pointed by a simple wind vane, while large turbines generally use a wind sensor coupled with a servo motor. Most have a gearbox, which turns the slow rotation of the blades into a quicker rotation that is more suitable to drive an electrical generator. Since a tower produces turbulence behind it, the turbine is usually positioned upwind of its supporting tower. Turbine blades are made stiff to prevent the blades from being pushed into the tower by high winds. Additionally, the blades are placed a considerable distance in front of the tower and sometimes tilted forward into the wind to a small amount. In this slide is listed the relative merits of horizontal axis wind turbines. The main advantages of the horizontal axis wind turbines are efficiency is higher than vertical axis turbines. These are self-starting, less expensive to install. The technology is better developed through continuous research and readily available commercially. The main disadvantages, however, are important parts of the horizontal axis wind turbines require maintenance which is very high, and there is a requirement of yaw mechanism to turn the turbine into the wind. Here is a collage of vertical and horizontal axis wind turbines. Some designs are already in application and some are proposed and modeled. These are counter-rotating wind turbines which have two facets, both have three blades. And the second is highway wind turbine, and the third is light pole wind turbine. Here is a map which provides an estimated summary of wind speed at 100 meters above the surface level. The map is derived from high-resolution wind speed distribution based on a chain of models which downscales wind from global models, approximately 70 km, to mesoscale, approximately 9 km, to microscale, approximately 150 meters terrain. The output resolution is 1 km. We shall now discuss about the wind farms. A wind farm is a group of wind turbines in the same location used for the production of electric power. A large wind farm may consist of several hundred individual wind turbines distributed over an expanded area, but the land between the turbines may be used for agriculture and other purposes. For example, in the Gansu wind turbine, the largest wind farm in the world, has several thousand turbines. A wind farm may also be located offshore. Almost all large wind turbines have the same design, a horizontal axis wind turbine having an upwind rotor with three blades attached to a nacelle on the top of the tall tubular tower. In a wind farm, individual wind turbines are interconnected with a medium voltage, often 34.5 kV power collection system, and communication network. In general, a distance of 7d, that is 7 times the rotor diameter of the wind turbine, is set between each turbine in a fully developed wind farm. At a substation, this medium voltage electric current is increased in voltage using a transformer for connection to the higher voltage electric power transmission system. There are mainly two kinds of wind farms: onshore wind farm and offshore wind farm. We will see these in detail in the upcoming slides. The onshore wind turbine installations are generally built in hilly or mountainous regions and tend to be on ridges, generally 3 kilometers or more inland from the nearest shoreline. This is done to exploit the topographic acceleration as the wind accelerates over a ridge. The additional wind speeds gained in this way can increase energy produced because more wind goes through the turbines. The exact position of each turbine matters because a difference of 30 meters could potentially double the output. This careful placement is referred to as micro-sitting. Here in the picture is shown two wind farms. The picture in above is the San Gorgonio Pass wind farm in California, United States. This famously windy slot between the San Jacinto and San Bernardino mountains is a perfect place for harvesting wind. No wonder this spot is covered with turbines of all kinds and ages. On a windy day such as this, it's fun to see all the turbines going at full speed except for the broken ones, and how the wind energy is really extracted to harvest electricity. The picture below is the Gansu wind farm in China, which is the largest wind farm in the world in the list of onshore wind farms. Here is a pie chart representing wind energy harvest in Asia as of installed capacity by the countries in 2015. China leads the league, followed by India, Japan, South Korea, Taiwan, and rest of the Asian countries, which collectively produce 862 megawatt, that is 0.5%. Wind power generation capacity in developing countries like India has significantly increased in recent years. As of 29 February 2020, the total installed wind power capacity was 37.669 gigawatts. This is fourth largest installed wind power capacity in the world. Wind power capacity is mainly spread across the southern, western, and northern regions of India. Wind power costs in India are decreasing rapidly. The levelized tariff of wind power reached a record low of rupees 2.43, that is 3.4 cents US dollars per kilowatt hour without any direct or indirect subsidies during auctions of the wind projects in December 2017. In December 2017, the Union government announced the applicable guidelines for tariff-based wind power auctions to bring more clarity to minimize the risk to the developers. This wind power amounts for nearly 10% of India's total installed power generation capacity and generated 62.3 terawatt-hour in the fiscal year of 2018 to 2019, which is nearly 4% of the total electricity generation. 70% of the annual wind generation is during the 5 months duration during May to September, coinciding with southwest monsoon durations. In India, solar power is complementary to wind power as it generated mostly during the non-monsoon period in the daytime. Here in this slide is listed the relative merits of onshore wind farms. The main advantages are the onshore wind farms last for approximately 20 years. These are cheaper to install and construct the foundation. The cost recovery can be met in 2 to 3 months of installation. Cheaper cost of integration to electrical grid network. The main disadvantages are these are noisy, sometimes unpleasant to aesthetic beauty to the landscape, and it occupies farmlands and meadows which could be otherwise utilized for producing crops. The offshore wind power refers to the construction of wind farms in larger bodies of water to generate electrical power. These installations can utilize the more frequent and powerful winds that are available in these locations and have less aesthetic impact on the landscape than land-based projects. However, the construction and the maintenance costs are considerably higher. Siemens and Vestas are the leading turbine suppliers for offshore wind power. As of October 2010, 3.16 gigawatts of offshore wind power capacity was operational, mainly in the northern Europe. Offshore wind power capacity is expected to reach a total of 75 gigawatts worldwide by 2020, with significant contributions from China and the US. The UK's investment in offshore wind power have resulted in a rapid decrease of the usage of coal as an energy resource between the years 2012 and 2017. As well as there is a drop in the usage of natural gas as an energy source in 2017. In the year 2012, 1,662 turbines at 55 offshore wind farms in 10 European countries produced 18 terawatt-hour, which was enough to power almost 5 million households. As of September 2018, the Walney extension in the United Kingdom is the largest offshore wind farm in the world at 659 megawatt. The Walney offshore wind farm is a group of offshore wind farms 9 miles away in the west direction of Walney Island in the Irish Sea, England. The location is shown in the map. Another example of offshore wind farm is the West Duddon Wind Farm, and the location is shown in the map. West of Duddon Sands Wind Farm, occasionally known as West Duddon Wind Farm, is an offshore wind farm located 14 kilometers southwest of Walney Island in the Irish Sea, England. The wind farm gets its name from a large sand bank uncovered at low water in the mouth of the estuary of the River Dedon to the north of the Furness Peninsula. The farm usually lies to the southwest of the Dedon Sands and covers the area approximately 67 km squares. The farm covers an area with 108 operational units providing a production capacity of 389 megawatts. Ormonde Wind Farm is another wind farm located nearby the two previously discussed wind farms. This wind farm is located west of the Barrow-in-Furness in the Irish Sea. The wind farm covers an area of 8.7 square kilometers and has a total capacity of 150 megawatt and is expected to produce around 500 gigawatts of electricity per year. Denmark was a pioneer in developing commercial wind power during the 70s, and today a substantial share of the wind turbines around the world are produced by Danish manufacturers such as Vestas and Siemens Wind Power, as we discussed in the previous slide, along with many component suppliers. In Denmark's electricity sector, wind power produced the equivalent of 47% of Denmark's total electricity consumption in the year 2019, which increased from 43.4% in 2017 and 33% in 2013. In the year 2012, the Danish government adopted a plan to increase the share of electricity production from wind to 50% by the year 2020 and 84.0% by the year 2035, thus replacing all possibilities of producing energy from fossil fuels and other resources. Denmark had the fourth best energy architecture performance in the world in the year 2017 according to the World Economic Forum, and the second best energy security in the world in the year 2019 according to the World Energy Council. Here is a picture of Middle Grunton offshore wind park, which is 3.5 kilometers outside the city Copenhagen, which is also the capital of Denmark. When built in the year 2000, it was the world's largest wind farm in the offshore wind park category. Here is shown a comparison of offshore and onshore wind capacity in Europe as of the year 2017. The offshore wind capacity generated 15.8 gigawatts, which contributed 1.5% of the offshore wind in European Union's power generation demand. The capacity factor for the average offshore wind energy is 41.7%. On the other hand, the onshore wind capacity generated 152.9 gigawatts, and this contributed 10.1% of the onshore wind in European Union's power demand. This is 22.5% of the average onshore wind capacity factor. Here is some models of wind turbines, onshore as well as offshore wind energy farms. The land-based and shallow water wind turbines up to 30 meters depth is a proven technology and has been harvesting energy. On the other hand, the transitional waters up to the depth of 30 to 60 meters offshore and deep waters more than 60 meters are still under demonstration and research. The offshore wind turbines have two categories, namely fixed offshore wind turbines, which have a variety of designs already in usage. These are monopile bases, tripod base, jacket base, suction caisson base, and gravity base. On the other hand, there is another design which is called floating offshore wind turbines, and it has different kinds of installations at the base, namely ballast stabilized spar buoy with catenary mooring drag embedded anchors and mooring line stabilized tension leg platform with suction pile anchors and buoyancy stabilized barge with catenary mooring lines. The key difference between onshore wind farms and offshore wind farms is the different environment of their locations. As a result, offshore wind farms must be provided with submarine cables for the energy transmission. The anchorage of the offshore wind platforms at the seabed is a very crucial point that has to be taken care of. Establishment in the seabed engineering is a very highly researched area nowadays. Here is the picture of world's second full-scale floating wind turbine and the first to be installed without the use of heavy lift vessels. WindFloat operating at rated capacity of 2 MW, approximately 5 km offshore of Paua de Varzim in Portugal. Here is a collection of some more pictures of full-scale floating wind turbine models. These are considered to be high-efficiency, large power generation systems and could be controlled by cables anchorage at the seabed. Here in the picture is demonstrated how the offshore floating wind farms work. The huge floating wind turbines, each about 600 feet tall, are grouped together and anchored to the ocean floor, as we have seen some models in the last slide. Then electricity from the turbines is transmitted to a floating substation. The electricity then flows through the buried cable to an onshore power plant and distributed to the power grid. The relative merits of offshore wind farms are listed here. The main advantages are these installations are stronger than the onshore counterparts. These last for a longer number of years, which is 25 to 30 years. These produce 50% more energy than the onshore counterparts. During strong winds, it produces 3 to 5 megawatt per hour. These receives higher and more constant wind speed at the site. The most prominent advantage is these save onshore land and spaces which could be used for agriculture and other purposes. However, there are some disadvantages which are these wind farms are more expensive to build, more difficult to maintain and access, and sometimes detrimental to the marine life. Here is shown two pie charts displaying top 10 countries by added wind capacity in 2019 and top 10 countries by cumulative wind capacity by the year 2019. In the year 2015, there were over 200,000 wind turbines operating, with a total nameplate capacity of 432 gigawatts worldwide. The European Union passed 100 gigawatt nameplate capacity in the year September 2012, while the United States passed 75 gigawatts in the year 2015. China's grid-connected capacity passed 145 gigawatts in the year 2015. In the year 2015, wind power constituted 15.6% of all installed power generation capacity in the European Union, and it generated around 11.4% of its power. World wind generation capacity more than quadrupled between the years 2000 and 2006, doubling about every 3 years. In this regard, China has been rapidly expanding its wind installation in the late 2000s and passed the United States in 2010 to become the world's leader. As of the year 2011, 83 countries around the world were using wind power on a commercial basis. A small vertical axis wind turbine on the roof of a house is shown here in the picture. It measures 3 meters in diameter and 5 meters in height and has a nameplate rating of 6.5 kilowatt. Small-scale wind power is the name given to the wind generation systems with the capacity to produce up to 50 kilowatts of electrical power. Isolated communities that may otherwise rely on diesel generators may use wind turbines as an alternative. Individuals may purchase these systems to reduce or eliminate their dependence on grid electric power for economic reasons or to reduce their carbon footprint. Wind turbines have been used for household electrical power generation in conjunction with battery storage over many decades in remote areas. This is ideal for running a small household-scale business entrepreneurship as well. Now we shall continue to the fourth and the last part of this lecture.